Okay, so this applied problem, I've changed the numbers, but it's still the same idea. You can follow the steps with me, just put your numbers in place. So it's about inflation. Part 1 says, oops, here, I meant to change everything to 4%. Part 1 says you got a home that's worth $300,000. How much will it be worth next year using 4% inflation? So what you're doing is you're just calculating 3% more of, sorry, you're calculating 4% more of $300,000. So there's a quick way of doing that. You can just multiply by 1.04. The 0.04 is the decimal form of that percentage. Okay, so if you ever need to increase a number by 4%, multiply by 1.04. Or you could do it the old-fashioned way, take 300,000 times 0.04 and then add that back to 300,000. Okay, 2 steps there, but with my method, just 1 step. Okay, so it's going to be worth $312,000 in a year if that's inflation. Okay, there's obviously a lot of other factors, but with inflationary dollars, if everything else remains the same, expected to be worth $312,000 next year. The time of making this video, inflation's out of control. It's even bigger than 4%. Usually inflation's around 2%, though. I think that's what all those economists say is a good, healthy economy. Part 2 says if you have a house that's worth $300,000 today, how much will it be worth in 2 years using 4% inflation? So to do this, you could repeat the same calculation. You just got to multiply it by another 1.04. Just take what you had in part 1 and increase it by another 4% again. So what's happening is you can rewrite this using powers because you're multiplying by the same thing, 1.04 twice. And that's the pattern we're going for. Because in part 3, we're supposed to create a function. It's supposed to be a function that represents how much money our home is worth, the value, after a certain amount of years. Okay, so that's how we start a function. This is the range variable, this is the dependent variable, and this is the independent variable. So this means you plug in a value for t, and we'll give you the value for v. You plug in a number of years, and it will spit out the value of the home. And so this is like your y variable. And that equals $300,000. The pattern that's going on here, every time you go up by another year, you multiply by another 1.04. So we should be doing 1.04 to the t power. And this is how you would type out t powers with that caret key. Shift 6 gets you that key. Okay, so that's the function that we need here, because I'm increasing by 4% each year. Look, if you plug in 0, after no time has elapsed, it spits out 300,000 like it's supposed to. If you were to plug in 2 in here, it would spit out what we got in part 2, 324,480. Part 4, using 4% inflation, how many years will it take until the value of the home is doubled to $600,000? So let's use that function that we just came up with, except this time we're not plugging in a value for t. I'm going to draw this one out. We're plugging 600,000 in for the value of the home and for v of t. Okay, remember that t isn't multiplying. That's function notation. This is v of t is how you'd say that. We plug in 600,000 in for the entire left side, and that equals 300,000 times 1.04 to the t power. That's the setup. So to get t by itself, we've got to get rid of this 300,000. It's multiplying to 1.04, right? So the opposite would be dividing. So you're going to get 2 equals 1.04 to the t power. And now to get a variable out of the exponent position, you need a logarithm. It doesn't matter what logarithm, as long as you do the same logarithm to both sides. So I'll just use natural log, because it's one less letter. Could use common log, log if you want. You could use log base pi. I don't know why you would, but you could. Okay, so use natural log to both sides. And now that lets this exponent come down and multiply. So we got natural log of 2 equals t times natural log of 1.04. Okay, so to finish getting t by itself, I need to divide that 1.04 from both sides. But you could change these to decimal values in your calculator. Right? 2 natural log is blah, blah, blah. 1.04 natural log, same thing. Much, not the same thing, but a bunch of decimals. So I'm going to copy what natural log 1.04 is, because I know I need to type that in second in my calculator. Okay, so it's natural log 2. There's natural log 2 divided by what I got from natural log 1.04. So that's 17.67 years is how long it would take to double. And part 5, it says if inflation is 4%, how much should you get in a raise for salary so you have the same purchasing power? Look, let's say you spent every single dollar of your salary on bananas, right? Because of inflation, if banana prices, if the value of a banana was to stay the same, meaning like the supply didn't change, the next year you would be able to buy 4% less bananas if your salary didn't go up because of inflation, right? Maybe you could buy 100,000 bananas this year. Next year you're going to buy, because it's 4% less, I should be able to do that in my head. You're going to be able to buy 96,000 bananas because of inflation. Okay, so how much of a raise should you get? I don't want to reveal the answer, but it's using this number 4%. I mean, I feel like I'm not teaching anything unless I tell you, look, your salary's got to go up by 4%, right? Or else you're not going to be able to buy the same amount of bananas. We need to be getting raises that are consistent with inflation, or else we can't buy as much with our dollar today as we can with our dollar a year from now. So a 4% raise is what we need.